You could substitute it in the other equation and cancel BL out of this, and now you get the induced voltage and current equals mg nu. So of course, what is voltage times current? Watts. So we've got, there's our watts, and again, we can measure the other thing we can measure really well is acceleration of gravity. We've got special instrumentation that can measure that down in parts in 10 to the 9. So isolating all those variables, we have our balance, our power or our watt balance, and we can isolate and now solve for mass out of that process. Yes?
Is this done in like a temperature-controlled environment?
Oh yeah, yeah. That's in fact, it's the NIST watt balance is in its own building, so it's got a very specialized temperature control system, and it's specifically made to be isolated so there's no stray magnetic fields anywhere near it as well. It's a pretty special setup in that process, but there's a lot of wrapped around temperature control in the experiment too. Yes.
This measurement involves the acceleration of the gravity g,
yes,
which is not necessarily to be a constant, and it could change because the Earth is not isolated. Would that cause any trouble?
Oh, so what they do is they're measuring localized gravity. So it's not using the universal constant as much as what is the exact acceleration of gravity at that physical location, because you're right, gravity, there's actually quite a bit of variation of local gravity around the world in that. For example, between Indiana and Phoenix, Arizona, the acceleration of gravity varies by about 1/10% because it's not just the acceleration of gravity between the difference from the center point to the Earth to where you're on the surface. So your elevation is part of that equation, but also the centripetal acceleration of where you are horizontally on the Earth as well. You'll have no force if you're sitting on the North Pole, but if you're out at the equator, you have quite a bit of additional force in that to consider. And then there's lots of things about different densities, different mass densities that are close to that. Actually, the oil field exploration, that's how they search for oil, is they look at localized gravity, and that's why we've got instrumentation that it gets very good, again, down to parts per billion in that measurement process.
So a gravitational measurement at the same time they're making.
Yes, yeah. Well, what they do at probably, I think they do it before and after, but because over short periods of time, it's going to be essentially the same, but it's in that physical point on Earth when they're doing the measurement. Then they do look for, is there some sort of seismic activity that might shift that gravitational field pole in that process. So you're right. That's where it goes into managing all of the different sources of uncertainty out of this process. And you'll see that also in the experimental results where we refine measurements and find some more errors and take some more errors out and get better uncertainties on these results as well. So that's the watt balance experiment, but I did want to mention the Avogadro project, which is the International Avogadro Cooperation on this, which is back to the atom counters. So what they've tried to do realistically on this is to grow a absolutely perfect crystal of silicon. Why silicon? Because silicon is something we've had a lot of practice for semiconductor work, building really good crystals, okay? Then we want to polish it, we might want to make it perfectly round. And you've probably seen the things say the world's most rounded object, and it is pretty amazingly round for a device on that. But there are some takeaways in this process as well. For one, the crystalline structure of silicon is polyhedral, so you'll never get round, no matter how hard you try. And also, it's really difficult to understand the oxide layer that forms, the silicon oxide layer, and measure that and deal with that. And then, even then, you've got to assume that you've grown a perfect crystal, and they use X-ray density measurements to determine how perfect the structure is or how many atoms are missing in that crystalline structure. But they've actually gotten really good results out of that too. So this is...
I have a question.
Yes.
So financially, for a new country coming in, you said that the UN sends people to help them get their measurements standardized.
Yes.
What's the trade-off of, so clearly one doesn't require super cooled electronics. Is was that something that they would try and like provide for them in the future if they chose that one? Or?
No, that's a really good question. So it depends. You're right. You only need to measure as good as you need to measure. So if you're in Kenya, for example, Kenya doesn't have a Josephson voltage system. They don't have a need. Their uncertainty for their best voltage is they actually use what we call a transfer standard. And it's funny that transfer standard is manufactured by Fluke. And every lab around the world uses that. And what we do is we could hand carry that to, say, the National Laboratory of Germany that has the quantum standard. We characterize this value down to about a tenth or 2/10 of a part per million, hand carried back to there, and now they could use that standard to disseminate traceability for quite economically for their country. And then there's like Egypt that used that method for quite a few years until they built up their economy and built up their background enough that they could afford a Josephson voltage system. So you're right, it's something that there's only about 50 countries around the world that might have the Josephson system out of 200 or so countries. So everybody else will use the Fluke transfer standard for their volt to realize their national volt. Is that kind of, does that answer your question? Good question. But all of these measurements, by the way, if you saw on the volt, you saw clearly that Planck's constant goes back to this. So we really think that the definition will fundamentally, and it also pops back into the Avogadro experiment too. So it's really the definition of Planck's constant is what the key role in this is. So this is the measurements this is the experimental measurements we've had over the last few years of Planck's constant. So you can see that back in 1998, this is NIST's measurement with their watt or Kibble balance. So that's what KB NIST 98 stands for, Kibble balance, NIST 1998. Here is the X-ray crystal density measurement from IAC, which is the International Avogadro Cooperation, back in 2011. So you can see smaller error bars over here. Here's NIST back in 2015. So you can see they found some uncertainty and some errors in their balance and made a better measurement. Here's the IAC measurement in 2015. Here's NRC Canada in 2017, best measurement. They've really nailed it with their watt balance. The IAC in 2017, that is their value for the X-ray crystal density. And here's NIST in 2017. So you can see where NIST has gotten better and better and better, and our uncertainty's gotten much better as well. Here's where they took that silicon sphere and sent it to Japan and let Japan make an independent measurement of the X-ray crystal density. So NMIJ in 2017, the National Laboratory of France has now gotten involved because, and back to your point on the watt balance, there's only about 3 or 4 watt balances around the world that are working as well, because this is even higher than the high in that process. Yes.
Question. So you're getting better and better uncertainty, right?
Yes.
But in the sense of the measurements, it looks like they're also different within the uncertainty.
Yes, they're independent experiments, which is good science. You're exactly right. So, and on that, and I'll just finish this, but I'll get to that answer because that's exactly the problem or what we had to get down to. And by the way, the least sum of squares that CODATA uses for the international accepted value for Planck is kind of based upon these experiments right now. But you're right, we need. So before we moved from the kilogram, the International Committee on Weights and Measures, which is the organization that oversees the global measurement process, they put 2 requirements for us to move away from the kilogram. And one was we had to have 3 independent experiments that all agreed to within 5 parts in 10 to the 8. Because now we're getting down to the uncertainty that we saw the kilogram drifting in the first place. And one of those experiments had to be better than 2 parts in 10 to the 8th independently for its uncertainty. So we have, I believe, 5 values now, five experimental values that are within 3 or 5 parts in 10 to the 8th, and we've got a couple of them down within 2 parts in 10 to the 8th. So now you're right, it's not perfect out of this, but the issue is, have we measured it so far that the uncertainty in this is less than the uncertainty we're living with the kilogram today? So is it perfect? No, and maybe 50 years from now, we'll need another fine adjustment down in parts in 10 to the 9, right? But that's exactly what we're doing right now and again, I've been very involved since 2011 with this process. And in fact, we thought, oh, we'll have this done in 2012, and then That comes along, no, 2013, no, 2014, no, and it's not official yet. So now all the data is in. We've got all this, they've kind of drawn a line saying, everybody, pop quiz is over, turn your paper over, test is done. And we've got the experimental results into measure. So in November of this year, and they have determined their value for Planck's constant based on this proposed value that the International Committee of Weights and Measures will meet in November. And now I would say, though, it's pretty much a slam dunk at this point that they will accept this value. But they could flip. They could change their mind and not accept. They could say we need to do more work. But if everything goes as planned, on May 20th of 2019, we will change our value for Planck's constant, and we will change the definition, which I'll explain a little bit more in a moment on that. By the way, why May 20th? Because that's the anniversary of the signing of the Treaty of the Meter. That's what we would celebrate every year as World Metrology Day. Look it up. Who has a fun time with it? We have a little party each year for that. So, but wait, there's more. There's a little bit more than the kilogram. There's also some issues with the Kelvin, okay, for its measurement. So the Kelvin is presently defined as 1,273.16 of the triple point of water, the point in which water exists in all three phases, solid, liquid, and gas. However, that's under the condition of water being sealed in a quartz container, evacuated to 611.2 pascals, and it has to be Vienna standard mean ocean water, and this is the isotopic content, sorry for the eye strain, but it's got a very, very specific isotopic content for this water, so it's kind of a beast making these standards. And why can I say that?